Welcome to a story about the material that built the modern world and the crisis it has inadvertently created. We are surrounded by it, in our homes, our cars, and even our clothes. But today, we are looking beyond the convenience of plastic to examine its afterlife. This is the story of polymers and plastics, and the unfolding global emergency known as the microplastic crisis. To understand how we got here, we must first understand the chemistry of the material itself. At the heart of every plastic object is a chemical structure known as a polymer. But what exactly are polymers? In scientific terms, they are large molecules, often called macromolecules, which are composed of many smaller repeating structural units. Think of them as long chains. It is important to realize that not all polymers are artificial. Both natural polymers, like DNA, cellulose, and proteins, and synthetic ones, like plastics, exist side by side in our world. To build these massive chains, nature and chemists alike start with a single, simple unit. This brings us to the monomer-polymer link. Monomers are the small single molecules that act as the individual links in the chain. They link together to form polymers. A classic example of this transformation is ethene. Ethene is the monomer that, when linked together in massive numbers, forms polyethylene, the most common plastic in the world. The process of turning monomers into polymers is called polymerization, which is essentially the art of building chains. There are two main ways chemists achieve this. The first is addition polymerization, where monomers add directly to the growing chain without losing any atoms. This is how we get polyethylene. The second method is condensation polymerization. In this process, monomers join together but release a small molecule, like water, as a byproduct. These reactions are the engines of the plastic industry. So when does a polymer become plastic? We define plastics as synthetic polymers that are solid at room temperature and, crucially, can be molded into various shapes. This moldability is what makes them so versatile. The common types we see every day include polyethylene, PE, polypropylene, and PET. These materials are the backbone of modern life, used extensively in packaging, textiles, and construction. However, the very feature that makes plastic so useful, its durability, is also the cause of the longevity problem. Chemically, most synthetic plastics are non-biodegradable because they possess incredibly strong carbon-carbon backbones. Nature simply doesn't have the tools to break these bonds efficiently. As a result, plastics can persist in the environment for hundreds or even thousands of years, accumulating faster than they can ever disappear. While plastic doesn't biodegrade, it does break up. This process is called the breakdown photodegradation. When exposed to the elements, UV radiation from the sun attacks the polymer matrix, causing the long polymer chains to become brittle and fragment. Over time, a single plastic bottle fractures into thousands of tiny pieces. This process effectively converts macroplastic items into hazardous microplastic particles. This fragmentation leads us to the central villain of our story, microplastics. Scientists define these as plastic fragments or particles measuring less than 5 millimeters in size. Because they are so small, they are easily transported and difficult to clean up. Today, they are ubiquitous, found in oceans, freshwater systems, soil, and alarmingly, even in the air we breathe. Where do these particles come from? We categorize them into two sources. Source 1 is primary microplastics. These are plastics that are manufactured to be already less than 5 millimeters when entering the environment. They are intentional pollutants. Common examples include the abrasive microbeads found in exfoliating cosmetics and the microscopic plastic fibers that shed from synthetic clothing during washing. The second category is often more visible in its origin. Source 2 is secondary microplastics. These particles are formed from the fragmentation of larger plastic items like bottles, bags, and fishing nets. As these large items weather and break apart, they generate billions of particles. Consequently, this is the largest source of microplastic pollution globally. Once these particles enter the water, they face a specific environmental fate. Microplastics are transported globally by ocean currents, traveling thousands of miles from their source. Eventually, they accumulate in 5 major ocean gyres, massive swirling vortexes of water. Here, they remain suspended near the surface, where they wreak havoc by blocking sunlight and affecting the photosynthesis of phytoplankton, the base of the marine food web. Not all plastic floats. We must also look at environmental fate, sedimentation, and soil. Denser microplastics typically sink to the ocean floor, where they accumulate in coastal and deep-sea sediments, creating unseen plastic dumps. On land, the problem is just as severe. Microplastic particles from treated sewage sludge are widely used as fertilizer, meaning they are increasingly found contaminating agricultural soil. The biological cost of this pollution is staggering. Health Impact 1 involves the ingestion by marine life. Because of their small size, microplastics are available to organisms at the very bottom of the food chain, like zooplankton. As these particles are eaten, plastics can block digestive tracts, leading to starvation. These effects don't stop there. They climb the food chain as predators eat prey, accumulating plastic at every level. The danger isn't just physical blockage, it is chemical. Health Impact 2 is chemical leaching. As they degrade, microplastics leach toxic chemicals that were added during manufacturing, like phthalates and bisphenol A, BPA. Furthermore, in the environment, they act as sponges, attracting and concentrating hydrophobic environmental toxins like DDT and PCBs on their surface, making them poisonous pills for any creature that eats them. Eventually, this pollution circle reaches us. Health Impact 3 is human exposure. The evidence is undeniable. Microplastics have been found in bottled water, tap water, salt, beer, and even the air. For humans, ingestion occurs primarily through consuming contaminated seafood and inhaling dust and air. While we know we are eating plastic, ongoing health research is racing to understand the long-term consequences. Confronted with this crisis, humanity is seeking solutions. One path is recycling and waste management. We desperately need to be improving infrastructure to collect and process waste effectively, preventing leakage into the ocean. Beyond mechanical recycling, scientists are developing chemical processes to actually break down polymer chains back into reusable monomers, closing the loop on plastic production. Another promising avenue is the development of biodegradable and bioplastics. Instead of oil, we can create bioplastics derived from biological sources like maize starch. The goal is to engineer biodegradable plastics that are specifically designed to be broken down by microbial activity under specific conditions, ensuring they don't persist for centuries. Technology alone isn't enough. We need governance. The solution also lies in policy and legislation. Governments are increasingly banning single-use plastics like bags, straws, and cutlery to stop the problem at the source. Furthermore, they are implementing extended producer responsibility, EPR, laws which enforce end-of-life disposal accountability, making manufacturers responsible for the waste they create. In summary, we face the great challenge. The longevity and widespread use of polymers have created a global environmental crisis that respects no borders. The sheer scale of microplastic pollution requires a multifaceted approach, technological innovation, global cooperation, and significant behavioral change from every one of us. Ultimately, the only way forward is a fundamental shift in our economy. We must embrace the conclusion circular economy model, We must stop the linear habit of moving away from the take, make, dispose model. Instead, we need a system built on sustainable recycling and reuse. We must prioritize designing materials that can be safely recycled, reused, or naturally decomposed, ensuring that the materials of the future do not become the pollutants of centuries to come.